Thanks for coming out. I really appreciate it. I know many of you, and I have given talks like this before, and you've heard me do the 3 S's of climate change, but Wally asked me if I would add a 4th S today, which is spiritual. So simple, serious, solvable, and spiritual. Try to do all 4. This will be a challenge because, that's more stuff than I usually talk about, but it is kind of odd that I would call this problem simple because it's complex in many ways, right? This is a scientific problem, it's a technological problem, it's a social problem, it's a spiritual problem. They're all interrelated. We just heard we have to transform the world economy faster than we've ever done before. Oh my gosh, how can we call that simple? But what I'm going to tell you is that the scientific side of this is very simple. The stuff that I spent 30 years on, that part of it is simple. Maybe that's why I chose to spend 30 years on it, because it's easy. I'm joking. But it's basically stuff that you learned in grade school. And I just want to remind you that you already have all the science background you need to understand the crux of this issue from a scientific point of view. And then we'll move on to serious, which is what's bad about it, solvable, which is what needs to be done about it, and spiritual, which is sort of why we need to do this. So do you ever wonder why day is warmer than night? Why summer is warmer than winter? Why Phoenix is warmer than Fargo? If you think about it, just for a moment, the same answer to all 3 of these questions. The answer is because heat in minus heat out equals change of heat. If you put more heat into things than you take out, they warm up. If you take more heat out than you put in, they cool off, right? You already knew this. This is why a pot of water warms up when you put heat into the bottom of it. This is why when the sun beats down on the ground in the morning, the temperature goes up. This is really fundamental, not just to the climate system or the weather, but to everything, right? The addition of heat to things causes them to change their temperature. All of the heat coming into the world comes from the sun. Maybe you learned, like I'm suggesting, some of this goes back to grade school. There's 3 ways to move heat around. I'm not going to test you. It's conduction, convection, and radiation. Conduction is like if you stick a nail, foolish enough to stick a nail into a fire, eventually you're going to have to drop the nail, right? Because the heat is conducted along the material of the nail. But conduction takes material, a conductor. The Earth is floating in a vacuum, so there's nothing to conduct the heat to. You can't get rid of heat by conduction. Convection is like where hot air rises from a campfire because it's buoyant, carries the heat upward. Cold air comes in to fill its place. But you can't convect heat away from the Earth because gravity, thank goodness, holds the air against the solid Earth, and therefore there's no way to get rid of the heat by just blowing it off into space with the air. So it really leaves only radiation. Again, electromagnetic radiation is the only way to get heat in and out of the Earth. The radiation from the sun warms us up, but if that was the whole story, the Earth would just get hotter and hotter and hotter without bound. Eventually it would melt and boil and vaporize and it'd be the end of the world. That hasn't happened, therefore that's not the whole story. There is heat that gets out of the Earth. The heat has to pass through the atmosphere. It's invisible. Makes it hard to believe in. Let me remind you, you know about this kind of heat. It's infrared radiation. If you ever turn on an electric burner on the stove, eventually it gets cherry red. But before it gets cherry red, you can feel the heat coming off of that burner. That's infrared radiation. It's light, but in a different wavelength that our eyes can't see. And the Earth radiates this invisible heat out to space, and that's what carries the heat out that compensates for the sun coming in. And there are these molecules of air that get in the way. So I apologize to those of you who've already seen this silly little demonstration, but almost all of the air, 99%, is made of molecules that have 2 atoms of the same element. So it's N2 and O2. This is nitrogen and oxygen. We breathe in, the oxygen gets used up, we breathe back out, but the nitrogen is basically just passing in and out without doing anything. Electromagnetic radiation going up through the atmosphere can interact with these molecules. Molecules are made of atoms. Atoms are made of protons, neutrons, and electrons. See, I told you I was going to remind you of this stuff. So the protons and neutrons on either end, the nuclei of the atoms, the electrons, some of the electrons are shared between the atoms. That's the chemical bond. The radiation can come up. It's a magnetic field. It accelerates the charged particles back and forth. They kind of go woo, 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 woo. They don't really make that sound. I just make that part up. but the vibrational energy of the molecule has now is converted from the electromagnetic radiation has been converted into vibrational energy of the molecule. But because 99% of the molecules in the atmosphere have just two atoms and they can only vibrate in that one direction, that's it for the ways that they can interact with radiation. A tiny number of molecules in the atmosphere have three atoms instead of two. It's quite rare. It's way less than 1 in 100 molecules that have three atoms. But the most abundant of them are CO2 and water vapor. So I do my funny little thing here. Only got the two hands, so let's this be carbon dioxide, okay, CO2 molecule. And just like O2 and N2 can absorb that radiation, go woo, 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 or back to its ground state, whoa, 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 by releasing a photon. But there's more, because CO2 is not identical on either, or it's identical. It's got three atoms instead of two atoms. It can go beep, boom, beep, boom, beep, boom, beep, boom, whip, whip. Each one of these different ways of wiggling the molecule absorbs a different wavelength of infrared radiation. That's what makes CO2 a greenhouse gas. Water vapor, H2O, has got a bend in it. It's even better at these sort of dances than CO2. These gases there are simply more ways to rearrange their geometry than there is for O2 and N2, and therefore they absorb well in the infrared part of the spectrum. And basic common sense explanation here, well, I think maybe all of you are old enough to remember incandescent light bulbs. So these are 4-watt light bulbs. You know, back when I was a kid, they were Christmas tree lights. And then when my kids were little, we used them for night lights in the hallway, and they would find their way to the bathroom, right? It was a 4-watt incandescent light bulb. And if you double the number of these beep-boo molecules up in the sky that interact with the radiation, that would add this much extra heat, 4 watts, to every square meter. This is about a square meter, right? This is maybe a half a square meter, this table. So imagine a 4-watt light bulb here and here and there and there and there and there and there. But not just this room and not just Fort Collins, but the entire world covered with little 4-watt light bulbs. And you're going to leave those 4-watt light bulbs on 24 hours a day, 365 days a year, forever. I mean, certainly for the rest of our lives and much, much longer than that. And if you did that, that would make the Earth a bit warmer, right? You know, maybe not a lot warmer because they're just 4-watt light bulbs, but they're every 3 feet. The whole world covered with little 4-watt light bulbs. Now, believe it or not, all of that was known before light bulbs were invented. The laboratory measurement of this effect was first published by John Tyndall in 1863, 160 years ago. He put CO2 and water vapor and methane, other different gases, in flasks and shined infrared light through them and measured the attenuation of the infrared light by different gases and different combinations and different pressures and so forth. Worked out all the math and actually predicted 160 years ago that if we burned enough coal, we would add enough CO2 to the atmosphere to dramatically change the climate. He even speculated that this was maybe the cause of ice ages, which didn't turn out to be true, but that was the discovery, really, of the CO2 effect on climate. It's not something that we discovered recently. It's not something that really has a lot of political involvement, because it was back during the US Civil War, right? This was not a big political issue at that time. And so it brings me to what I sort of consider the most common myth about climate change. And it's dangerous to tell people a myth because they're going to remember the myth. They're not going to remember that it wasn't true. Okay, so warning, I'm going to say something that's not true. The myth is that the reason scientists expect it to get warmer in the future is because it's been getting warmer recently, okay? And it has been getting warmer recently. Everybody's probably seen these graphs, right? It used to be colder, and then it got warmer, and then it got even warmer. And you get the idea when you look at a graph like this that we're arguing from extrapolation. Do you know that word? It's a big word. Means somebody shot a line through this thing out into the future and said, well, if this keeps up, it's going to get really hot. And that's true. If this keeps up, it's going to get really hot. But that's not how we figured this out. Remember, we knew this way before it started warming up. This was predicted in 1863. So it wasn't the warming, and it wasn't correlation to CO2, and it wasn't anything like that led us to this conclusion. Rather, we know that adding CO2 to the atmosphere will warm the climate because we know that when you add heat to things, they change their temperature. Okay? There's no question at all that CO2 absorbs the outgoing heat from the Earth. It's been measured for 160 years. The measurements have gotten better and better and better. They've been done thousands of times all over the world by many, many, many different people. The measurements are not just made in laboratories, they're made outdoors, they're made from towers, they're made from balloons, they're made from airplanes, they're made from satellites. There's really no question at all that adding CO2 to the atmosphere absorbs the outgoing heat and thereby traps heat within the Earth's climate system. And we know, of course, that adding heat causes changes in temperature. So this is a very, very well understood piece of physics that's completely in line with everything else that you know about the world if you've ever cooked on a stove or noticed the difference between summer and winter. Okay, so much for the simple part. Why is it serious? What does this mean for us as people? If we double the amount of CO2 in the atmosphere, it adds 4 watts of heat to every square meter. I talked about that. That warms up the world on the average about 3 degrees Celsius. Who cares, right? 3 degrees Celsius for the whole world. Doesn't sound like that much. First of all, it doesn't warm up the whole world evenly. Most of the world is ocean. And you can imagine a 4-watt light bulb sitting on top of the ocean. Maybe you can't because none of us live by the ocean. And even if you did live by the ocean, you're probably not aware that on the average the oceans are 13,000 feet deep. Very, very deep. So that 4-watt little light bulb on 13,000 feet of water doesn't change the temperature of the water very much. So most of the warming is actually on land. There's warming over the ocean, but the ocean warming is much less than the land warming. Therefore, the land warms up more than 3 degrees Celsius in order for the average to be 3 degrees Celsius. Turns out the land warms up about half again as much as the ocean. And the southern hemisphere is mostly ocean, the northern hemisphere is mostly land. So the northern hemisphere warms up more than the southern hemisphere. And then the third thing to know is that places that get snow and ice warm up more than other places because the snow and ice reflects the sun to space, keeps it cool. You guys know this if you ever, if we get a snowstorm in December, often it's cold for a month or more after that snow because it's reflecting the sun to space. So if you warm up enough to melt the snow and ice, then you get not just the 4 watts from the light bulb, you also get the extra heat from the sun that isn't bounced back off to space. So, you know anybody who lives on land in the northern hemisphere where it snows? Oh yeah, all of you. So you don't get global warming, you get extra. And in our part of the world, if we get really serious about cutting out fossil fuel, not just us, but the whole world gets serious about transforming the world economy, as Wally said, we can hold the warming to about 3 degrees Celsius in our part of the world. And if we don't get really serious by the end of the century, it'll be 6 degrees Celsius in our part of the world. Celsius doesn't make any sense to you, so I'm going to translate 1.8 Fahrenheit degrees for every Celsius degree. So that's, instead of 3 to 6, it's 5 to 10. Okay, so 5 degrees if we Fahrenheit if we get serious, 10 degrees by the end of the century if we don't, and then continues to get hotter after that. even 10 degrees doesn't sound too bad. I don't know, it's supposed to be like 85 today. So 10 degrees is 95. Actually, that's pretty toasty. But not just today, right? On the average, 10 degrees Fahrenheit. We don't have a good index in our head for what 10 degrees Fahrenheit of warming looks like unless you look at a map. So here's a map of the United States, average high temperatures in Fahrenheit, and each color is 5 degrees different. So if I say we're going to have 10 degrees Fahrenheit of warming, it means you're moving 2 colors on the map. There's Denver, and if you move Denver 2 colors on the map, it's Albuquerque. Oh man, that's actually pretty different. I don't know if you've ever been to Albuquerque, but it's different there. It's hot there. Their winters are mild. Maybe that's a good thing. But if you were a farmer in Lamar or Lyman, and you swapped out the climate of Albuquerque for the climate of eastern Colorado, you would absolutely notice that, right? You would, first and foremost, you would notice because of water. You would need more irrigation water to be able to sustain your crops, to sustain your livestock, for that matter, to sustain suburbia and cities and urban civilization here. If you moved everybody 600 or 800 miles south from where they are today. Around here, we don't really need to go hundreds of miles to encounter different climates. We know that all we have to do is go up and down the mountains, right? The topography is sort of a quick and easy surrogate for us for warming and cooling. We live on the Great Plains, and then there's the Ponderosa up above us, and then the lodgepole and the spruce fir and the tundra and so forth. And it turns out in Colorado, every 3,000 feet of elevation produces about 10 degrees Fahrenheit of warming or cooling. So if you want to be in a place with 10 degrees cooler average temperature, you just go up 3,000 feet. So when I say that, there's plenty back here.
I'm good.
You're good. Can't see the slides?
Well, that's true. Sorry, you guys.
That's all right. So every 3,000 feet is about 10 degrees Fahrenheit. 10 degrees Fahrenheit is like taking the climate, not the whole climate, but the average temperature of Denver and moving it up to Estes Park. The average temperature of Estes Park and moving it up to Trail Ridge Road. So you can imagine what that would do. And in fact, at the end of the last ice age, there was about 10 degrees Fahrenheit of warming here. And all of these zones kind of marched up the mountain. You can imagine, as the ice retreated out in, Canada and all that, Scandinavia, the tundra sort of marched up to the top of the mountains, and the lodgepole moved up, and Ponderosas moved up. Everything moved up 3,000 feet. But that warming took 100 centuries, 10,000 years to happen. And we're talking about doing it in 1 century. So the same amount of warming, but 100 times faster. And of course, the trees and plants and animals and so forth don't have time in 100 years to move up. They don't have legs. They can't just walk. They actually have to reseed and grow and reseed and grow, and it takes many, many, many generations for the plants and animals to move up. We happen to live in a place that's quite vulnerable to warming because of the water situation. We do have enough water, but we only just have enough water, if you will. This is a map of the western United States. The colors indicate the annual amount of precipitation, rain and snow. Just like in real life, most of that map is brown. And we got 75 million people that live in this part of the United States on this map. And the reason we can support 75 million people in all our cities and our farms and our ranches and our society here is because of these blue places on the map. And you know what those are called? Mountains. The mountains stick way up in the sky, and they catch the water vapor, turn it into snowpack, and that snowpack accumulates all winter long, and it's like a giant reservoir, and it comes dripping down in the spring, and it fills up our water supply. That's where we get our water supply. And if you warm the climate 10 degrees, if you sort of shift all those zones up by 3,000 feet, that dramatically reduces the amount of winter snowpack accumulation that you have to tap to water a society of 75 million people. Climate people, I don't know what you call it, more like paleo archaeology kind of people have done these tree ring things. So this is tree ring. Sorry, it's kind of a complicated graph. Goes back to the year 1000. This is for the Central Plains, and this is for the Southwest. And you know, tree rings are fat in a good year, and they're skinny in a bad year. And they've sort of worked out these relationships, paleoclimate in our region over 1,000 years. For example, back in the 12th and 13th centuries, there were these very long, severe droughts in the Southwest that really set back the Anasazi, drove them to the mesas, and changed the whole civilization of the Southwest. More recently, in the 1930s, there was the Dust Bowl that impacted both the Central Plains and the Southwest. And then these are projections out to 2100 from a whole slew of climate models, and you can see that because of the extra heat and extra evaporative demand, the projected drought in our region just dwarfs anything that has been seen in this region for the last 1,000 years. Much, much, much worse. And it isn't so much the lack of water, it's that the extra demand for water, extra evaporation coming from the landscape due to the 10 degrees warmer temperature. So very, very serious impact on drought. The other thing I'd want to talk about is fire. Think about our forests. You know, they get a big slug of water in the spring with the snowmelt, and then that water basically saturates the soils. The pore space in the soils is full of water, and then all summer long the trees are evaporating water out through their needles, and they're taking that water in from the soil pores that filled up from the snowmelt. By the time you get around this time of year, September, they've basically finished, used up the water they can draw from that snowmelt that came at the beginning of the season. Ground gets all crunchy underfoot. This is the time of year that it's particularly vulnerable to burn. If you raise all those zones by 3,000 feet, they wind up using much more of that water every single day, and they're going to run out sooner. Forgot to put that. Evaporative demand increases, and the season of evaporative demand is longer, right? The warm season, instead of starting in, let's say, May and going to September, you may be going from April to October, even March to November, something like that. The burning season gets longer. The third thing is, you know those really bad days that I'm thinking 2012 here, where it's like, 100 degrees in the shade and 3% relative humidity and it's 40-mile-an-hour winds. Those kind of days happen much more often in a hot summer than they do in a cool summer. So for all three of these reasons, you expect greater wildfire in a warmer climate. In fact, the National Research Council looked at this in 2011. And for our part of the mountains, something like a 650% increase in wildfire per 1 degree Celsius of warming. So you can imagine if we had 3 or 4 degrees Celsius of warming, this is thousands of percent more, more than 10 times the amount of wildfires in our mountains. And in fact, many of these projections, it looks like the forest just can't be sustained under a warmer climate. Just like it happened at the end of the Ice Age, all those zones move up, but you don't have time to move the trees, and they wind up just burning and being replaced by stuff like cheatgrass and yucca and things like that. One more bad myth, and then hopefully I'll get on to some happier stories. And I kind of hate to beat you up with all this stuff, but this is actually pretty important and a little hard to understand. The myth is when we stop burning fossil fuel, the CO2 will go away. And let me just explain two really important things here. Firstly, CO2 is not a reactive gas, okay? When we think of air pollution, you think of the brown cloud in Denver, you think of the smog. The reason air pollution is bad for us is because it's chemically reactive with our bodies, right? It irritates your sinuses, it gets in your lungs. My mom died of COPD. She had irritation in her lungs from air pollution. She'd have to close her windows on the days that they'd have high ozone days. CO2 is not like that. CO2, there is no further degradation of the CO2 molecule. It's completely oxidized. It's the thermodynamic ashes of the carbon cycle. There's no more reaction to do to it to get it to break down into something else. That means it just accumulates in the atmosphere. The only way to get rid of it in the long run is that it has to dissolve into the oceans. But the oceans, 13,000 feet deep, have a layer on top that's buoyant, that's warmed by the sun, that floats on the top of the cold water underneath. So the big bulk of the oceans, but more than 90% of the oceans, never touches the air. So it can't dissolve the CO2, except where it gets super cold at the poles, where it gets cold enough to sink. And it takes about 1,000 years for the oceans to turn over and come to chemical equilibrium with the atmosphere. So it'll be thousands of years before the CO2 will go away, after we stop burning it. Now, some silly graphs here. These are not predictions. These are simply what-if calculations. Here's the year 1800. Thomas Jefferson was president. Here we are now, 2019. Here's the year 2300. That's about halfway between Captain Kirk and Jean-Luc Picard. Okay, so this is a very long stretch of time here. Here's CO2 emissions, and you are here. The CO2 emissions are about 10 of these units. Here's the amount. The CO2 itself is in blue, and it's gone up, but hasn't gone up very much. It's gone up about 40% over what it was pre-industrial, and the temperature's gone up, but only a little bit. So you are here on these maps. The trouble is, if we keep growing the world economy with coal, oil, and gas, we will triple the amount of CO2 emissions in this century. So we're on track to triple the amount of stuff we burn, and that's primarily through economic growth in parts of the world that are trying to climb out of dire poverty. That would raise the CO2 concentration to not twice pre-industrial, but 4 times. So not one 4-watt light bulb, but 2 4-watt light bulbs on every square meter of the earth pretty much forever. And then I did this what if. What if on January 1st, 2100, Happy New Year, you turn it all off, right? Or you discover, dilithium crystals, nuclear fusion, some kind of thing, and the emissions go to 0. Unfortunately, the CO2 does not follow, okay? And the warming even slower. So the changes are essentially permanent. Basically, we got a thermostat with a ratchet in it. You can turn it up, but you can't turn it back down. It really only goes one way. The changes that we make in this generation and the next generation are essentially permanent changes on a historical timescale. Eventually it goes away, but it may take 100,000 years for it to all go away. So we're talking about changes that will apply for many, 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 many generations, hundreds of generations perhaps. It's pretty scary. But it's solvable, okay? I gotta tell you that from a technical point of view, it's solvable. From an economic point of view, it's solvable. This is not the end of the world, and we know what to do. So, I don't mean to be facetious, but there's really one simple thing to do. Stop setting stuff on fire. Right? It's burning carbon that makes the CO2. The CO2 is a permanent addition to the atmosphere. It changes the transparency of the atmosphere with respect to heat, and that's got to stop. And then we've got to wait a very long time for this stuff to go away. It's not going to go away right away. There's basically 2 ways to get to stopping burning stuff. One is to figure out how to live well with less energy. And the second is how to make energy that doesn't involve setting stuff on fire. So however, it's got to be done pretty fast. This is an estimate for how to hold warming to 2 degrees Celsius globally. Basically emissions, so this is the amount of stuff we burn, has to fall by half in the next 10 years, and then fall by half again in the next 10 years, and fall by half again in the next 10 years. Basically every 10 years you got to cut the amount of burning in half forever. That's not easy. I want to talk about a little bit about how that works. The amount of CO2 we emit, there's some math here, sorry, but it's very simple math. Let me walk you through it. 4 numbers, 1, 2, 3, 4, and you're going to multiply the 4 numbers together. It's pretty straightforward. This is the population, the number of people in the world. This is the amount of economic activity per person, the GDP, if you will, the amount of dollars spent, or earned per person. The amount of energy it takes to make a buck, and the amount of CO2 it takes to make a unit of energy. And you can see that it's true because the E cancels the E and the dollar cancels the dollar and the P cancels the P and just get CO2 equals CO2, right? This is not rocket science here. It's pretty straightforward. So more people having more wealth, using more energy. Energy is made from CO2, therefore CO2 comes out. So everybody's heard about population. I'm going to just sort of correct you a little bit on that. You may not have thought about this. This is world population back to 1750, and here we are today. This red line is the rate of growth of this blue line, okay? When I was in high school, the population was growing 2% per year. World population was growing 2% per year. Now it's half of that. Did you get that? World population is growing half as fast as it was when we were kids. Population has doubled in my lifetime, and it will never double again. The world is on track to having zero population growth in this century. That is not what's driving fossil fuel emissions higher. It's not population. It's people growing out of poverty, okay? Which is a good thing. So these are two pictures taken from the same spot. You can see the clock tower here. This is Shanghai. And the two pictures were taken 20 years apart. Shanghai has more people in the city limits than any other city on earth. About 23 million people live in the city limits in Shanghai. It's surrounded by suburbs. Each of the suburbs has more than 10 million people, and you've never heard of one of them. Shanghai Metro is about 75 million people. And this is not population growth. This is dramatic economic growth in 20 years. Shanghai went from being a decrepit third world city to like the financial capital of the world in a generation. The size of the Chinese economy grew 20-fold in 30 years. Absolutely incredible. You know, they're talking about a slowdown in the Chinese economy. Chinese economy is expected this year to slow down to 6% annual growth. Wow, right? I mean, I don't know that the US has ever seen 6% annual growth. It's an amazing fast-growing economy. And, you know, India's right behind them, and then Africa's behind there. Between China and India and Africa, there's about 15 times as many people as there are in the United States. So it's really people growing out of poverty that are driving this up. Let me talk a little bit about the energy use side. Remember, we talked about population, we talked about economic growth. When you think about energy, mostly we think about our cars. However, I want to invite you to think instead about buildings, because it turns out that energy use in buildings is about half of the energy use in the developed world. And by energy use in buildings, I'm including, you know, mining the ore, smelting the steel, forging the steel I-beams, transporting them on site, hanging those I-beams, operating the building, heating, air conditioning, ventilation, the whole 9 yards. So roughly twice what we use in transportation is used in buildings. And luckily, there's lots of room for improvement here. This guy, Ed Masria, came to CSU some years ago, and this is one of his slides. These are projections of energy use in buildings, which is, remember, half of energy use in the United States, out to 2030. This is a prediction made by the US Department of Energy in 2005, in 2007, 2009, 2011. You see what's happened here is that we don't expect to use anywhere near as much energy in buildings as we did 10 years ago. And the reason is because architects and designers have gotten smarter about building buildings. We have better lights, we have better ventilation, we have better doors and windows and air conditioners and all that kind of stuff. And just this one change alone, in the United States alone, is going to save us $4.5 trillion by 2030. It's a total win-win, right? This is money that we were just throwing away before, and now we're not. We're capturing that money by investing it in smart architecture that saves us phenomenal amounts of money in the long run. So buildings are a tremendous piece of low-hanging fruit. In fact, Masria and his group, Architecture 2030, have started a compact among architects. All the commercial architects in the world have signed on to this, that by 2030, they will not design any building in any country on earth that is not a net zero energy building. So that means that all the energy used to construct the materials and build the buildings will be regenerated by that building itself and put back out on the grid. The building will have a net zero energy footprint over the life cycle of its building. That's half of our energy in the developed world. That's an amazing accomplishment and almost universally accepted across the world of large commercial architecture. Now on the generation side, again, these are kind of complicated, but I want to sort of show you some predictions made out to 2025 for how much new solar was going to go on the grid and how much new wind power was going to go on the grid. So these are sort of expert predictions. There's a prediction made in 06, 08, 09, 10, 11, 12. You see what's happened is each year these so-called experts take whatever was built this year and just forecast that that's how much we're going to build every year forever. What? How can they be? Sorry, this is a church. I have to be careful what I say in here. But clearly these are wrong, right? And they're not just a little bit wrong. They're crazy wrong. Year after year after year, these guys are predicting that the future will be like the past in terms of the kinds of energy. When in actuality, what's happened are these black lines that have gone up more than 10 times faster than anybody predicted, even sort of the world's experts. How can they be so crazy? How can they make these silly predictions? The reason that they've been so wrong is that the prices of renewable energy have fallen much, much faster than anybody expected. So this is the price of solar panels. This is the year I graduated high school, 1977. Solar panels cost $77 per watt in the year I graduated high school. Solar panels now cost 30 cents a watt. Okay, they're 200 times less expensive than when I was in high school. It doesn't feel like that long ago to me that I was in high school. Imagine if other things were 200 times cheaper than when I was in high school. Imagine if cars were 200 times cheaper than when I was in high school. Amazing, right? So this has completely changed the equation in terms of the economics because the energy is much, much cheaper. Germany went from 4% wind and solar on their grid in the year 2000 to 32% in 2016, eightfold increase. This is the amount of sun that falls in a year in Germany. This is how much sun falls in a year in the United States. Germany gets less sun than Alaska. And Germany did a 700% increase in solar and wind in 15 years. If we got serious about doing this in like Alamosa, oh my gosh, we have like an incredible amount of very, very cheap energy. In Colorado, last year, Xcel Energy looked at closing 2 huge fossil fuel coal-fired power plants in Pueblo, 600 megawatts of electricity in Pueblo, because they were at the end of life, those plants. And they went for open bids on the open market for replacing that electricity, 600 megawatts, fully expecting to put in gas-fired replacements for the coal. But it turned out that the wind plus batteries came in cheapest. In fact, the median price, so 50% of the bids were below this, the median price for wind plus batteries was 2 cents a kilowatt hour for Xcel Energy. That's half of what they were paying to operate the coal-fired power plants they already had bought and paid for. So just the coal cost twice as much, never mind the plant, right? Just the coal itself cost twice as much as building brand new wind power with battery storage from scratch. It's amazing. And this is not some sci-fi future. This is last year here in Colorado. Now, it is going to cost some serious money to do this massive transformation that Wally talked about. Economists estimate that it'll cost about 1% of the global economy to completely convert everything off of fossil fuel and onto other stuff. 1% of the, so what do I mean 1% of the global economy? You take the total value of all the goods and services produced in the world in a year. Okay, that's called the gross domestic product. Maybe you've heard this term, GDP. The GDP of the whole world currently is about $85 trillion a year. Okay, it's kind of just crazy big number, right? 1% of that is $850 billion a year. It's a very large amount of money. 1% of the world economy is about what it cost our ancestors to retrofit all the world's cities with indoor plumbing. Okay, now think about if you had to do that today, right? Dig up every street in New York, London, Paris, Tokyo, lay sewer lines. Knock out tenement walls 20 stories high, put in hot and cold running water. knock out internal partitions in every apartment in all those cities and put in toilets and sinks and showers. Just think of the labor, right? It would be staggering to do that. And our ancestors did that, and they didn't run out of money doing that. Imagine what it did for plumbers. Imagine what it did for plumbing suppliers. Imagine what it did for the grocery store down the street from the plumber, or the children of that plumber who could then use that money to go to college, right? So money is never gone in capitalism. It gets circulated. It gets used over and over again. And we are so glad that our ancestors invested 1% of the world economy, because now we have toilets and sinks and showers. You know, it's a good thing. Just to put these costs in context, 1% of global GDP, okay, it's a huge number. Around 800 billion a year. Just cell phones. Who in this room bought a new phone in the last 12 months? Oh my gosh, there are 3, 4, okay. Just brand new phones. Not talking data plans, not talking minutes on your cell phone. Just the phone handsets themselves cost $600 billion a year, okay? And that's okay. We pay it because we want to. The US military, $665 billion a year. New cars. How many bought a new car in the last 12 months? Not very many. Okay, you guys need to get out and support your economy more. Just the new cars to $2,000 billion a year. So that dwarfs the amount of money it would take to solve the climate crisis. Roads. $320 trillion we have spent, we collectively, on roads. This is not the end of the world kind of money. This is the kind of money people spend. These are my grandparents. That's Max and that's Francis. And it was their generation, of course, that did the indoor plumbing thing. And when they were done with indoor plumbing, they did rural electrification and fought the Nazis. And you know, each of these projects was gigantic, huge, more than 1% of the world economy kind of projects. Not only did they not go broke doing those things produced all of the economic growth in the first few decades of the last century. These are my parents, Margie and Bob. Their generation did giant infrastructure projects, right? They built the interstate highway system. They fought the Cold War. They sent people to the moon. Amazing, right? These were all gigantic projects. And they produced economic growth and jobs and prosperity, and that's what drove the economy through the 20th century. This is myself and my wife back when I had hair. And our generation spent enormous money, trillions and trillions of dollars, putting PCs on every desk, on every office in the world. And then when we were done with that, we built the internet. And when we were done with that, we replaced all the landline phones in the world with cell phones. I mean, these are giant, huge projects, bigger than replacing the energy system, and yet we didn't go broke doing these things. This is what everybody did for a living, really, this is my whole adult life. These are my kids, and they get to do it again. They get to replace aging infrastructure with infrastructure that's not going to destroy everything. And that's going to provide all of the jobs and all the prosperity in their generation, just like it has before. Now, I'm going to talk a little bit about the spiritual nature of this problem. I'm going to start with this woman who's a philosopher, Kathleen Dean Moore. She's at the University of Oregon, and she's written this incredible book, which I highly recommend. In fact, you were asking me about books. Have a look at this one. Moral Ground. It's a series of essays by world leaders. So, for example, the foreword is by Reverend Desmond Tutu. There is an essay by Barack Obama. There's an essay by the Pope. There are about 100 of these essays in here. The question she asked all of these thinkers was, what do we have an obligation to future generations to steward the world as it is? And she gave me a different way of thinking about this. She calls it the missing second premise. Okay, so this is, maybe this isn't spirituality. This is more like ancient Greek spirituality, right, with logic. So we got a premise that science says this is how the world works. This is the way the world is. And then sometimes we think that the response to that has to be policy. Then this is what we will do. But Professor Moore showed me that there's something missing here. To get from this is the way the world is to this is what we will do, you need to ask the question of values. This is the way the world ought to be, right? Well, how should the world be? What do we want from our world? I want to take a different tack. You guys ever seen this movie, The Perfect Storm? So by analogy, there's this amazing book by another philosopher, Stephen Gardner, A Perfect Moral Storm, the ethical tragedy of climate change. And he really has sort of three things. The Perfect Storm book and movie was about 3 big storms that came together to make this superstorm that killed these fishermen. The perfect moral storm of climate change has 3 parts. There's a global storm, an intergenerational storm, and a story of moral corruption. The global storm means that the people who suffer most are the people who have contributed least to the problem, okay? The greatest suffering by billions and billions of people who really didn't cause this problem in the first place. The intergenerational storm has to do with the many thousand-year lifetime of CO2 in the atmosphere, and the moral corruption problem has to do with our individual tendency to sort of let ourselves off the hook here. The global storm is a little bit, it's pretty easy to understand. These are estimates of how much reduction in economic activity is expected in different countries by the end of the century due to climate change. The blue places like Canada, Greenland, Soviet Union, Russia, are places that are cold now, which will actually benefit economically from a warmer climate. The red places typically are places that are hot now, which will be harmed by a warmer climate, and in much of the global south, absolutely enormous economic impacts. Even averaged globally, something like a 25% reduction in the size of the world economy. So remember I said 1% of GDP to fix it, 25% of GDP is the consequence of not fixing it. So it pays off $25 to 1 to fix this problem. The people in Africa, in South America, in Southeast Asia, where almost all of humanity lives, are the people that take it the hardest. I've already kind of talked about the intergenerational storm. Just to put it in a little bit of perspective, here's how much heat in minus heat out has happened back to 400 million years ago. We have it in our power, it's really us and the next generation, to add more heat to the atmosphere than has been added over 400 million years. We have the capacity, if we burned all the fossil fuel, to turn that ratcheted thermostat up higher than it's ever been in this very, very long period of time. The last thing I want to talk about is moral corruption. The danger that billions and billions of people on Earth today face, and more importantly, 100 generations of future people face, is easy to deny. We have a nice life. I've got a nice house. I've got a nice car. It's a beautiful morning. I've got, a pretty good deal going on here. So I would rather not think about all those other people. I would rather just think about me. There's also an opposite of denial, which is despair, which is sometimes, I think it's almost like nihilism. I encounter people, I'm going to debate a guy on Wednesday he says there's no problem, we don't have to worry about this. But there's another side of this problem, which are people that I encounter on the political left who will say, oh, there's nothing you can do. It's all rotten to the core, just let it all collapse. It's over, it's hopeless. It's just as bad, right? There's this one, it's like you're driving down the road and you've already passed the sign that says bridge out, and you're flying through wooden barriers left and right, and the guy on the one side is saying, oh, don't worry about it, it's a hoax, the bridge isn't really out. And the guy in the back is saying, oh, it's hopeless, my wife left me, just go over the cliff. I don't want to hear this, right? So resignation and despair are just as bad as denial. We also have a tendency to go for these very small sort of personal gestures. I turned on my thermostat, I recycled my plastic bags, I did my thing, I rode my bike, now I'm good. No, this is a harder problem than that. Cleaning up my own life. Sure, I should ride the bike, right? I should take the bus, I should do all those things. But ultimately, the whole world's got to stop setting stuff on fire. And if you're not working for that, you're part of the problem. Is there hope is the wrong question. This is from a writer that I really admire, Dave Roberts. There is no such thing as game over, or too late, or no hope. It is certainly not the case that we have only 12 years to act. This fight will last beyond any of our lifetimes. The stakes will always be enormous. Time will always be short. There will never be an excuse to stop fighting. Think of it like this. There's two stories you can tell about history, about the meaning of human existence. One story is a familiar story. It's based on extraction, okay? Our world is based on stuff we dig out of the ground. Our modern standard of living, there's value in a lump of coal. Somebody sells it to a profit to somebody who sets it on fire, who sells the energy for a profit, who takes that energy and makes it into products and services, and you buy and you sell and you wheel and you deal and you get yourself an $85 trillion a year global economy. And maybe that's true. I mean, I get it. It stands to reason, this stuff. But let's hope that's not the true story of humanity, because that story is a tragedy. That story has a sad ending. That story says that when we stop burning coal, either because we run out or because we decide to, our descendants will just shiver in the dark, right? All 10 billion of them will have to make do with candles and outhouses and everything again. That's just a terrible story. That's a grim vision of the future. I prefer to think that our modern lifestyle comes from in here. It doesn't come out of the ground. It comes from creativity and ingenuity and hard work. It comes from the sweat of our brows and the sparks in our souls. And we are not running out of those things, and neither are our children, and their future is bright. Thank you for your time.
We have questions. Pastor Rick, go ahead.
So, I was just talking about this with some of our Sunday school kids, our youngest kids. How do we help them? If we're leaving this problem to them, how do we help them to not only understand it, but engage with them in the solution to climate crisis?
What a great question.
I have an 8-year-old, so I want to help her, and I'm also the generation that needs to be helped.
Yeah.
And again, we have adult forum here, but we have all older people. But how do we engage in that?
Yeah. Oh, thank you.
A couple of kids in the back, by the way.
And there's some kids back. Yes. Yes.
Thank you.
Young people.
And you look like a young person
I
yourself.
am.
So I think this is a great question. I have a sort of tendency to look from this sort of airplane view of this problem, and I say that this is a problem that's going to go on for generations, and it's not okay for us with the older generation to just pass this on to your generation and say, deal with it. We were the ones that sort of got ourselves into this mess. We didn't mean to, right? It's not like we set out to ruin the world. Rather, we were just doing the normal things that we were asked to do, and now here we are in this mess, and we're handing it off to one generation, 2 generations, 3 generations down the road. We, as elders, have to step up. We have to do stuff like this. We have to hold forums like this. We have to engage. We have to listen to the young people. You mentioned Greta Thunberg, right? Oh my gosh, she's incredible. You did. She sailed over from Europe. She's going on tour around the U.S. talking about these issues from the point of view of what a 16-year-old sees this problem. I don't know that. I mean, I haven't got a list for you of what it is that I can do for your generation and your generation. But let's not shirk our responsibilities as elders. Let's step up and recognize that we had a formative role in this problem, and that it's probably, even though I'm getting kind of old and I'm going to retire from my job, I'll keep doing stuff like this till I die. Thank you.
No, thank you.